Hello everyone, my name is Guozheng from the Visualization Research Group at Peking University. Here I will present our work titled GoTree, a Grammar of Trivializations. This work was done in collaboration with Tian, Qinmei, Prof. McGuffin from ETS, and supervised by Prof. Xiaoru Yuan. Many techniques are available for visualizing hierarchical data. Up to now, treeviz.net has collected over 300 trivializations, and different trivializations are designed for variant tasks and application scenarios. Taking the file system as an example, to show its topological structure, the most commonly used trivializations are the intended list or node link diagram. However, if users are interested into the size of directories, they prefer to use tree map visualizations. Therefore, to understand the hierarchical data comprehensively, it is usually necessary to combine different trivialization methods together. Nowadays, we often use three methods to implement different trivializations. The first is based on a software library like D3, which support several layout algorithms and can be extended by the user. However, these methods have a steep learning curve and heavy programming burdens. The other strategies are declarative language like Vega and visualization authoring tools like Tableau. However, these methods are with limited expressiveness. So, for the visualization of hierarchical data, it is significant to solve these two problems. First, how to construct different trivializations efficiently. Second, how to switch among different trivializations flexibly. To solve these two problems, we propose GoTree. GoTree provides users with a high-level trivialization construction method. It firstly decomposes trivializations into components, and group different components will construct corresponding trivializations. Changing the components will switch among different trivializations. For example, changing the Cartesian coordinate system to the polar coordinate system will change to the radial layout. Hiding the links between the nodes and changing the circle to the rectangle will change the radial layout to the Sunburst trivializations. Next, I will introduce GoTree method in detail from three perspectives. First is what is a component we defined, how to decompose trivializations into the components, and the third is how to construct trivializations using the selected components. The components we defined in GoTree are divided into three categories: coordinate system, visual elements, and layout. Coordinate system includes the Cartesian coordinate system and the polar coordinate system. Visual element includes nodes and the links between the nodes. Layout means the positions of visual elements in the coordinate system. The coordinate system and visual elements can be defined by users according to the desired trivializations directly. For example, the node link diagram in the right are defined in the Cartesian coordinate system. The nodes are circle, and links are straight line. Next, I will introduce the trivialization layout in detail. Many trivializations can be naturally implemented as a recursive algorithm. Based on this characteristic, we decompose one trivialization into multiple tree units recursively. Specifically, the layout within each tree unit are independent to the other tree unit in the trivialization results. Therefore, the layout of the trivialization can be transformed to the layout of multiple tree units. For example, as shown in the left figure, node link diagram and icicle plot are decomposed into 7 tree units on the right. For each tree unit, it consists of 2 candle components, the root node and the subtrees under the root node. In addition, we also define subtree group within each tree unit, which means a set of subtrees. With subtree group, we can define the tree layout using relationships, include the parent-child relationship, which means the relative positions between root and subtree group, and the sibling relationship, which means the relative positions among subtrees within subtree group. To further determine the layout of tree unit, we decompose the parent-child relationship and sibling relationship along each axis. The parent-child relationship is decomposed into 3 categories along each axis, include, juxtapose, and within. The sibling relationship is decomposed into 2 categories, align and flatten. Next, I will use node link diagram and icicle plot to explain our decompose method. For the node link diagram, its parent-child relationship along the x-axis is within, and y-axis is juxtaposed. Its sibling relationship along the x-axis is flattened, and y-axis is aligned. For the icicle plot, its parent-child relationship along the x-axis is included, and y-axis is juxtaposed. Its sibling relationship along the x-axis is flattened, and the y-axis is aligned. Previously, I have introduced what is the components we defined and how we decompose the trivialization into these components. Next, I will introduce how to construct the desired trivialization according to the selected components. Our method is parsing the specification into constraints. The variables of these constraints are the size and the positions of the nodes. Solving these constraints will get the attribute values of the nodes. And I will use include and flatten relationship along the x-axis as examples to explain our method. Include relationship indicate the relative positions between root and subtree group. Parsing the relationship can get 2 constraints. The first constraint we can get is the width of root is equal to the width of the whole tree unit. The second constraint is that the width of root is equal to the sum of subtree group and left padding, right padding. Flatten relationship indicates the relative positions among the subtrees within the subtree group. Parsing the specification can get 3 constraints. The first constraint is that the start position of the first subtree is equal to the start position of the subtree group. The second constraint is that the start position of the interior subtrees is equal to the positions of the last subtree plus its width and the margin. The third constraint is that the end position of the last subtree is equal to the end position of the whole subtree group. For more details about constraint parsing, please refer to our paper. The figure shows the whole computational pipeline of GoTree grammar. It starts from the hierarchical data. Decomposing the hierarchical data could get several tree units. Then, users input the specifications of the components of the desired tree realizations. After parsing the specifications into constraints and solving the constraints, we can compute the layout of each tree unit. Assembling the layout of each tree unit, we can get the layout of the whole tree realizations. And then we can render the final tree realization results according to the specifications of your elements and coordinate system. Based on the tree realization results, users can change the GoTree specification and change to another tree realization flexibly. We implement GoTree as an embedded declarative grammar within JavaScript. The format of GoTree is based on JSON. The figure above shows the Sunburst tree realization and its corresponding GoTree specification. Based on GoTree, we designed and implement a prototype system called Tree Illustrator to support users create tree realizations interactively. Users only need to select different components and adjust its parameters, then can construct the desired tree unit. Saving the tree unit into the template view and applying to the hierarchical data could get the final tree realization results. We create a diverse tree realization gallery using Tree Illustrator to demonstrate the expressiveness and generative power of GoTree grammar. Our gallery consists of not only existing tree realizations, but also novel tree realizations. For example, this tree realization can be space efficient to realize the non-parent-child relationship among the nodes in tree realizations. In addition, the tree units are independent with each other. Therefore, GoTree is suitable to construct the hybrid of different tree realizations. For example, based on the Sunburst tree realization and radial tree realization, we can hybrid these two realizations at the specific level to get the right top results, and at specific subtree to get the right bottom result. In the future, we plan to improve the expressiveness by supporting more intuitive nodes, explore the design space of tree realizations, and recommend the tree realizations for users according to the tasks and characteristics of hierarchical data automatically. In conclusion, we propose GoTree, a declarative grammar for creating a wide range of tree realizations, and Tree Illustrator, an interactive tree realization authoring tool. Thanks the above findings, and thanks for your attention. For more information, please visit our project website.